At VertiGrow, we aim to cultivate healthy and pesticide-free produce whilst hoping to conserve water and energy. By designing a self-sustainable farm, we are offering a long-term solution to food security in Qatar, utilising non-arable land, increasing productivity, and overcoming food shortages worldwide. The VertiGrow organisation was founded in September 2013. VertiGrow consists of a young and dynamic team bringing forward the most innovative ideas to overcome any problem at hand. The team consists of the following personnel: Howard Cox, who is the organisation's project manager and mechanical engineer; Greg Finlay, who is the team secretary and business and marketing manager; Russell Jackman, who is the structural and environmental engineer, with further responsibilities for the design of the CAD models; Matthew Ellinger, who is the lead structural engineer and the organisation's process manager; Owen Allen, who is the lead mechanical engineer and the group's energy specialist; and Richard Lewis, who is the lead geotechnical engineer. Richard is also the risk manager for the organisation. VertiGrow has a top-down organisational hierarchy. As project manager, Howard is responsible for finalising all decisions and providing team with direction. Greg Finlay manages external communications, providing a link from the team to the module leaders. Matt, Russell, Owen and Rich make up the workforce, striving to excel and create the next feat in engineering. 3 potential farm locations were considered. These were Qatar, Singapore and India. A decision matrix was used to finalise Qatar as the idyllic location. Qatar currently imports 90% of their food. The proposed farm would secure a locally produced food supply, thus greatly reducing their import costs. There is also future potential to overcome a food shortage in locations where people can't afford to import food. This is done by utilising knowledge gained from this project to enable vertical farms to be built in areas where traditional agriculture is impossible. The flexibility of the farm also allows a vast variety of crops to be grown. The vertical farm will be powered completely by renewable energy. The biogas facility utilises recycled waste to generate electricity, as well as providing heat energy and carbon-rich fumes which enrich the growing environment. The structure will be a 1000 kilowatt facility. When running at 90% efficiency, it can provide 8 million kilowatt hours annually. Any waste left over after the decomposition process can also be stored as compost. Finally, an additional gas storage will be constructed to regulate the gas supply from the digester to provide power during the digester regeneration. There will be a small-scale solar tower working in tandem with an array of solar panels. The solar tower utilises the heat of the sun to boil steam and power turbines. A 6 metre tall tower with just 3 metres squared of heliostats could produce approximately 7 kilowatts with plenty of scope for additional heliostats to increase power. The system utilises a molten salt reservoir to store excess heat, which is used to boil steam during low light conditions. An array of solar panels can provide roughly 5.5 kilowatt hours per metre squared a day, due to its high direct normal irradiance from an average of 9.4 hours of sunlight a day. The vertical farm will provide 8,750 tonnes of produce annually, from 15,600 metres squared of growing area and 2.5 million litres of aquaculture. This will be housed in a 7-storey building with a plan area of 60 by 70 metres, to give a total area of 29,400 metres squared. The proposed structural layout consists of the ground floor being designed from reinforced concrete and contains an agricultural setup, water filtration system, transport hub and cold storage. The 6 floors above have been designed as a steel skeleton with an electrochromatic glass shell. This glass is designed to allow light through while reducing the internal temperature. The hydroponic growing area has been designed for 12 separate growth cycles to provide weekly harvests. Hydroponic methods include rotary hydroponics. Rotary hydroponics uses natural light augmented with artificial lighting for optimum growing conditions. This technique is best suited to leafy greens and is optimised for a very short growing period. The artificial LED lighting is specifically designed to only utilise the red and blue light spectrums. This design results in a pink light being produced, which is optimum for the plants and reduces energy consumption. The secondary hydroponic growing method is direct water culture. This method relies almost entirely on artificial lighting and is best suited to long-term growing plants that need to be picked, such as fruiting plants. Harvesting and replanting will include modular plant trays to minimise harvesting and replanting time. This will maximise utilisation of the growth area. The design also employs a separate manually harvesting and replanting area for the modular trays, as well as cold storage area to prevent degradation. There will be an internal automated handling system to rapidly transfer produce between hydroponics, harvesting and replanting, aquaculture and packaging and distribution. A multi-zone climate control system will be installed to maintain temperature and humidity at optimum growing conditions for the plants and at a comfortable condition for workers. One of the main features of the project is the addition of the aquaculture system. This supports a stable stock level of roughly 250 tonnes of fish maintained by integrated fish breeding. The aquaculture and hydroponic systems work in partnership with each other, each providing the other with required nutrients through the aquaponic system. The design system harbours multiple fish breeding and harvesting cycles to keep stable stock levels and nutrient supply to the plants. The farm also utilises a closed water system, which drastically lowers water usage by 90% compared with traditional farming methods, by recirculating and reconditioning the water. The closed nature of the system also removes the need for herbicides and pesticides, which can cause significant damage to local ecosystems due to water runoff from fields. As such, the farm has a minimal impact on the local environment. Key project milestones for Term 2 are design of the closed loop water system, design of the structure, project report, marketing video, end of project presentation. To enable us to complete this timescale, funding is needed. The total funding necessary is to cover 3 months of work, including work into project management, design of the builds by engineers, and admin for support roles. This will cost just under £120,000. A risk assessment was undertaken to identify the risks for this project. The main risks for the project fall into 3 categories. These are change management, time management, and resource management. To conclude, this project is looking at gaining enough funding to enable us to complete our research into and the design of a functional, efficient vertical farm, increase food production and run completely from renewable energy sources. This project is currently being designed specifically for data to tackle a variety of different challenges across the globe which currently prevent traditional farming. Thank you for watching, and we hope this video has inspired you to invest in this project.